All right, in this example, example 1, what we're looking for is to find the eigenvalues and eigenvectors of this transformation. So we have t of xy is equal to negative x plus 2y plus 2z, 2x plus 2y minus z, that's a z, and 2x minus y plus 2z. Okay, so the first thing is to convert this into a matrix. And so looking at the rows and the columns, we have negative 1, 2, 2, 2, 2, negative 1, and 2, negative 1, 2. So this would be our matrix A, and we would multiply that by x, y, and z. And so if you multiply negative 1 times x, you get the minus x plus 2y plus 2y plus 2z. So that would be the first row, and that would give us the x value of the transformation, and the rest follows suit. Okay, so now that we have the matrix A, we can now use our tools to find the eigenvalues, and then we'll determine the eigenvectors. Okay, so we're going to construct the characteristic polynomial. So p of lambda is going to equal 0. That's what we're going to try and solve. So remember, p of lambda is the result of the determinant of a minus lambda I. Okay, and we set that equal to 0. Okay, so that is the process. So here is a. I'm going to subtract the lambdas. And the i's, remember, this is the 3 by 3 identity matrix for this case, since our transformation is 3 by 3. Which means that each of the diagonal elements is really going to be subtracting a lambda from it. So the result of this is going to become something of the form. I'm going to squeeze it in over here. So this is going to be negative 1 minus lambda, 2, and then 2. Then I have a 2 minus lambda, and then a negative 1, and then a 2, a negative 1, and then a 2 minus lambda. Okay, so I'm going to compute the determinant of this, and then set this equal to 0. Okay, so the determinant of this 3 by 3 is, all right, the determinant, you can find it a couple different ways. For this 3 by 3 case, you can actually do something by extending these two rows out and then doing the diagonal product. I just put this into GeoGebra, and I got that the resulting determinant comes out to be, so 0, carrying the 0 over from here, it gives me negative lambda cubed plus 3 lambda squared plus 9 lambda minus 27. Okay, so that's the result of carrying out the determinant. So now you can see we have a cubic function in lambda. So I'm going to factor out a negative lambda squared here. And I'm going to do some factor by grouping. So this is going to be positive lambda minus 1, no, minus 3 here. And then I'm going to factor out a 9 here. So plus 9 lambda minus 3. And this equals 0. And then common factor here. So I get negative squared plus 9. That's the terms left over. Factoring out a lambda minus 3 equals 0. And so it looks like we have a repeated root. So we're going to get lambda equals 3 and negative 3. You're going to get 2 lambda equals positive 3 from this one, plus or minus 3, and then a minus 3. So there's really 2 lambda values. So here are these are our eigenvalues. Okay. And so now that we have our eigenvalues, let's go ahead and determine what the eigenvectors are. Okay, I'll take lambda equals 3 first, since that's the first one I wrote down. So to find the eigenvectors, we're going to come back up to our matrix here with lambda being subtracted out, and plug that in and augment that with the null space. We're going to find the kernel of this matrix. As discussed in class, that's exactly what we're looking for. That's the condition that we need. So I'm going to replace each of these lambdas with 3, and then do row reduction on it to find the resulting equation. So if I plug in 3 here, I get negative 1 minus 3, so that's going to be a minus 4, 2 and a 2. Augment that with 0, 0, 0. Remember, we're solving the null space of this augmented matrix. Okay, 2, this is going to give me a -1 because 3 is positive, so 2 minus 3, and then -1, and then 2, -1, -1. Okay, so doing row reduction, I would put this in GeoGebra, but I think you can see pretty quickly that this row is exactly the same as this row. So if I just add or subtract these two rows together, row 2 minus row 3, that's going to give me, the top one's going to stay the same, -4, 2, 2, 0, 0, 0, and then 2, -1, -1, and this is going to be 0, 0, 0. Okay, so it looks like I can do maybe 2 times row 1 and add it to row 2. So 2 times row 1 and add it to row 2. So if I do that, then we have a new matrix. So this is going to stay the same, -4, 2, 2, 0. And then, let's see, so we have 2 times, oh no, it should be 2 times row 2 added to row 1, to row 2. And add row 1. That's what was confusing. All right, that looks better. All right, so 2 times row 2 and add that to row 1. That will reduce row 2. Okay, so 2 times row 2, that's going to be 4. Add that to a -4, so this is going to be 0. 2 times row 2, make that a -2, and I'm adding that to row 1, so that's going to make that 0, and likewise make that 0 and that 0. So we reduce all of this then to our, so this is our row reduced version, and so what this is saying is that x, well, you can say -4x plus 2y plus 2z is equal to 0. So if I maybe move the 4x over to the side and then divide by 4, you get x is equal to 1/2 y plus 1/2 z. Okay, remember, x and y and z are just parameters, they're arbitrary. Or another way of saying that is that this is equal to x, y, and z is equal to, well, we have 1/2, we have 1 and 0 for y, plus we have a 1/2, a 0, and a 1 for z. Okay, and since this is z, and since x and y, or sorry, y and z are parameters, then any vector of this set would be the eigenvectors for lambda equals 3. I guess I should have put that way over here. I should have put that this was lambda equals 3 was the, and so the lambda equals 3 has the vectors v1, which is going to be equal to 1/2, 1, and 0, and v2, which is equal to 1/2, 0, and 1. Okay, so those are our 2 eigenvectors for this eigenvalue, and then let's do the same thing for lambda equals -3. Okay, so for lambda equals -3, we're going to do the exact same thing. So we're going to plug it back into the matrix, and we had -1 minus 3, so -1 minus a -3. Okay, and then we had a 2 and a 2. We had a 2 minus a -3, and then a -1, and then we had a 2, -1, and a 2 minus a -3. Okay, we're going to augment that with zeros again. Okay, so this becomes, okay, this becomes, that becomes a positive 2 minus 1, so that's going to be 1, 2, and 2. This will be 2. That's going to become a positive 3, so 3 plus 2 is 5, and -1. And then we have 2, -1, and then a positive 5. And that's going to give me zeros here. Okay. Correction on this part right here, this should be a 2. Negative 3 becomes a positive 3. 3 minus 1 is 2. So I just made a quick mistake on that one. Everything else looks good. And so when I do row reduction on this, I get that, in much the same way, I get that the result is 1, 0, 2, 0, 0, 0, 0, 1, negative 1, 0, 0, 0. Okay, so that is the row reduced form, and so what that tells me is that I have x plus z equals 0, and I have y minus z equals 0. Okay, so z is the free parameter only in this one, and so what this is saying is that x, y, and z can be written in the form, well, if I let z just be z, that's going to be 1, okay, and then y equals z from here, and x equals opposite z, so it's going to be negative 1 z. So this, again, remember z in this case, and just like x and our y and z up here were just parameters. So then our lambda equals negative 3 has just the single eigenvector v3, which is equal to negative 1, 1, 1. Okay, so those are our 3 eigenvectors, and those are our 2 eigenvalues. Okay, I hope that was helpful, and I will see you in the next video.